Okay, good afternoon from 4 students. So welcome back again. So I see you again here. And I have one question here. This one no names on a one dot to me. Who is this? Dot to me. Now change to what? Rem. And the other one is only one word, only G. Can change your name, put your real name can or let me know lah. Because I need to know your name. No. Huh? How Punling? How are you? Okay, like this. So we start chapter 5. Okay, chapter 5 is wave. Wave here, a lot of things you study one, Wave, example is water wave, sound wave, light wave, and electromagnetic wave. All these are wave, water, sound, light, electromagnetic wave, okay? And for every this wave, you're going to study 4 big things, Maybe now you don't understand what I'm talking now. I might just have some idea first. First thing you're going to study is reflection. Second one is refraction. Third, you're going to study is diffraction. And the fourth one you're going to study is interference. You see now, for each wave, you study 4 things. Reflection, refraction, diffraction, interference. So you have how many types of wave? You have water, sound, light, and electromagnetic wave. Okay, 4 times 4, so becomes 16. So you have 16 things to learn in this chapter. Okay, a lot of things to learn now. You take 2 months, 3 months to finish one chapter. Okay, take a long time now. Don't worry that we are not behind time. We got enough time. Now it's only June, right? So still got enough time to count up all your syllabus. Don't need to worry so much, okay? So hopefully you all can go back to school fast, and then the tuition class, so you all can come. But right now, I don't know when the tuition class can on, No news from the government yet, okay? That's why I also did not open the tuition class yet for now. So still carry on with online class first, Okay? All right. So let's start our lesson now. I share the notes with you all, okay? First is this paper. How many of you got this paper? Chapter 5, wave. Got paper or not? Okay. This chapter got a lot of paper one, okay? Lesson 1, 2, 3, 4, 5, 6 all combined. Okay. So lesson 1 will be fundamentals of wave, the importance of wave. Second one is damping resonance. Maybe today only we do the lesson 1 only. This lesson 1, 2, I combine together because those days the old syllabus they make it separately, But now your new syllabus form 4 they divide it into 2. Actually, these 2 lessons actually those days is put it under one lesson 1, but now they split it into 2. Okay, so introductions of wave. Okay, now we look at this paper now. Okay, we go slowly bit by bit don't worry so much You all can relax a bit don't need to listen, then relax a bit don't need so worried, okay? Okay, let's look at the introductions of wave Oscillation can produce wave, okay? Highlight. Everyone knows, right? Vibration produces wave. All the wave come from vibration. Anything that vibrate will produce wave, isn't it? But in physics, we use the right term we call oscillation. Oscillation produce wave. Oscillation and vibration, same one, same meaning. Okay. Then highlight this. Wave transfer energy from one place to another without permanently displacing the medium through which they travel. Meaning that wave actually when they are moving, right? You see the water wave when they are moving, actually the wave transferring the energy from one place to another. They are transferring the energy without permanently displacing the medium through which they travel. For example, you see the water wave okay? Actually, the water wave, when the water wave come like this, right? From left, it move to the right. So it's transferring the energy from left go to right, the water wave, okay? But the object above the water surface, it won't move together when the wave is moving up, down, like that. That's why we say wave transfer the energy from one place to another without permanently displacing the medium through they are to travel. Meaning that only the energy transfer only. The molecule stay at constant position. For example, here I take this one to explain to you. You listen. I take this example for water wave. So the water wave is going up, down, like this, right? So when this water wave is moving, right, actually energy transfer the energy. But this molecule here, this molecule is not moving This molecule is only go up, go down, go up, go down only, vibrating only. Only the energy transfer from left go to right. The energy move. But the particles, the molecules, we say here, for example, this molecule will go down, and then it go up, go down, go up. This one also same, go up, go down. This is what mean by this statement. Wave transfer energy one place to another without permanently displacing the medium through where they travel. Okay, that is the meaning of wave. Okay, okay. When we drop a stone into a pond of water, you can see the stone drop into the water, then you can see the water wave come out, one circle, two circles, three circles, you can see the water come out, isn't it? When drop a stone into a pond, the kinetic energy of stone make the water surface move up and down near where the stone lands. Ripples spread outward. Okay, ripples spread outward means you can see when the stone drop, then you can see the wave come out one small circle, next circle, another circle, more and more circle come out. So it's spread out like that. So that is considered wave, Okay, move up and down near where the stone lands. Ripple, ripple means the wave Wave is, and ripple same meaning as wave Ripple spread outward. If any floating object on the water, some distance away will start to pop up and down. Meaning is this I can't draw here, How I going to explain? Maybe you all listen. Okay. Can you all listen? You all listen properly. Let's say in a swimming pool, there's a piece of leaf on the water surface. A leaf drop on it. Okay, then you throw a stone into the water. When you throw a stone into the water, you can notice the water wave come up. One circle, second circle, third circle. When the circle pass through the wave, pass through the leaf, can you tell me what happened to the leaf? Will the leaf move or the leaf just go up, go down, go up, go down only? I repeat again now, you listen carefully now. On the water surface, right, there's a leaf, a piece of leaf. The old leaf, dry leaf drop, then a leaf. Then I throw a stone into the water. The moment I throw a stone into the water, you can see the water wave come out. One circle, or more, a lot of circle come out, isn't it? The water wave. Okay, what happened when this water wave pass through the piece of dry leaf? The leaf will follow the wave move or just move up and down only the leaf. You understand what I say or not? Juling, do you understand what I say?
Yes, sir.
Juling, how do you think the piece of leaf, the leaf will move or just move up and down only?
Up and down only.
You say up and down only lah. Can one you what about you?
Up and down.
Yes, correct. So you see now, the water wave moving from left go to move out, but the leaf, you can see the leaf only go up, go down, go up, go down only. So very clear. So the water wave pass the energy, but it never displays the object. You see the leaf stay there, The leaf just go up, go down, go up, go down. That is the meaning now. The whole idea is here. You see, this on the water some distance away start to pop up and down, mean the water, the leaf go up, go down only lah. Okay, highlight here now. It is because the original energy of the moving stone has been transferred to the object by the wave motion. Okay, so you got the energy from the stone. The energy of the stone transferred to the water already, then the water wave come out, right? When we are at the seaside, this one another story, near the seaside, we can see large as well as small wave reaching the shore. You can see the water wave come to the shore, right? This wave arise because strong winds in the middle of the sea. Okay, strong wind. So the wind transfer the energy to the water. So the water got energy, so it become wave. The energy of the wind carried by the wave to the shore. This is the energy from the wind carried by the water as a wave to the shore. The water from the middle of sea does not reach the shore. Too far you cannot reach. Okay. The wave motion is regular and repetitive. Okay. For example, the wave the motion is regular, it's got certain pattern one, and it's repeat and repeat again one. It's repetitive, periodic motion. Okay. So for example, the water wave move up, down, like that, correct not? Now there are two types of wave highlight. We are going to study this one in detail, One is mechanical wave, such as sound wave, mechanical. Another one is electromagnetic wave. Okay. One is mechanical wave, the other one is electromagnetic wave. Okay, what is the difference between mechanical wave and electromagnetic wave? Okay, like this roughly you can jot down. Mechanical wave, right, cannot travel through vacuum. Jot down, cannot travel through vacuum. Mechanical wave cannot. Like sound wave, water wave, cannot go through vacuum. You need a medium to transfer. So that is called mechanical wave. Mechanical wave need a medium to transfer. With vacuum, cannot. Next one is electromagnetic wave. Electromagnetic wave is another type of wave. It can travel through vacuum. No need medium one, Electromagnetic wave can through vacuum. One example is sunlight. Sunlight from the sun can reach here, In between the sun and the earth, there's a big area is vacuum, no air one, right? But the sunlight can reach here because sunlight can go through vacuum. So remember now, mechanical wave cannot go through vacuum, but electromagnetic wave can go through vacuum. Okay. Okay, now another one, transverse. Okay, transverse wave. Slowly class. Transverse, and later on you learn another one, longitudinal. That's why I said this chapter is very long Okay, need a lot of patience to study everything here. Okay, transverse means I use this diagram to explain to you first. The wave is moving up and down like that, while traveling from left to right. You see, this arrow shows direction of propagation. Propagation means direction of motion. It moves from left to right, direction of propagation. And whereas the direction of vibration of particles, the particle is moving up, down, up and down. So you can see here now, The direction of vibration of particles and direction of propagation is 90 degree. This kind of wave is called transverse. Transverse means direction of vibration of the particle perpendicular to the direction of propagation. Propagation means direction of movement. Okay, it's 90 degree. Molecule move up and down, but the wave move from left to right is 90 degree. This is called transverse, Okay, you highlight here now. Wave in which the direction of vibration of particle perpendicular to the direction of propagation. So we call it transverse. So remember later on I ask you, remember now the definition. Transverse means direction of vibration of particle is perpendicularly to the direction of propagation. Propagation is a new word for you. Propagate. Propagate means a move. Direction of the wave movement. Propagation. Okay, can I understand here? Example now you see. Example of this kind of wave move up and down while moving left and right. Okay, highlight like water wave, water move like that, isn't it? Water wave, electromagnetic wave. Okay, electromagnetic wave is also considered transverse wave. Okay, electromagnetic wave has 7 components. All the 7 components you have to memorize on. Electromagnetic wave got 7. You see here, radio wave, microwave, infrared, light wave. Light is also considered electromagnetic. Light, ultraviolet, X-ray, and gamma ray. So altogether 7. 1, 2, 3, 4, 5, 6, 7. 7 wonder of the world. A lot of things in this world actually 7 one, You see the rainbow, 7 colors, right? 1 week we have 7 days. And then this electromagnetic wave also got 7 components. So only God can explain, 7. And not only that, 7 wonders of the world. In this world, the 7 wonder also 7. And this ocean in the world also. How many ocean in the world? Altogether, how many ocean? Also got big 7 ocean in the world. A lot of things 7 in the world, So I believe this 7 is a lucky number. But God created a lot of things in 7 one. Okay? And talking a lot of nonsense. You understand or not? Hashini, do you understand what I say? Hashini? Hashini, understand? No sound your mind. Commonly understand?
Understand, sir.
Understand, Okay, this Hashini say yes, but Hashini today cannot talk. I don't know why, the microphone problem. Or mic problem now. Okay, Hashini is okay, don't worry, Hashini. Okay, now I want you to remember the whole thing here. Transverse wave. What is transverse wave? What are the examples? Okay, before I let you memorize, okay, one more thing I need to explain now. Look at here. When the wave is going up, going down, going up, going down, right? Okay. Highest point is called crest. Highlight here, crest. The highest point is crest. And then the lowest point is called trough. T-R-O-U-G-H. These 2 terms you have to memorize on, Crest is the highest point. Trough is the lowest point. Okay? Highest point is crest. The lowest point is trough. But we don't say highest and lowest one. You say maximum displacement, positive displacement. This one go up is considered maximum. Displacement comes from this center line. The maximum displacement, positive displacement is crest. This one maximum also, but maximum negative displacement is trough. So remember this negative. This is maximum positive displacement. This is maximum negative displacement. So crash and trap, remember, huh? A lot of terms here, no? Okay, and now you go and memorize everything here. Okay, take some time, go and digest everything here. Okay, all right. You don't worry, don't worry. If you don't know the answer, you just say you don't know. Okay, no worry, no worry, don't tension. Okay, let me call names. Zhong Chao Yi, are you here? Zhong Chao Yi? Zhong Chao Yi here or not? Zhong Chao Yi are here now. Zhong Chao Yi, can you tell me now what is transverse wave? How to explain transverse wave? Transverse wave, how to explain? How you explain transverse wave? You don't want to talk, never mind, you type it up lah. Type out, okay? How to explain transverse wave? How to explain transverse wave? Okay, Ong Zhao Xiang, are you here? Zhao Xiang.
Yes, sir.
Zhao Xiang, you tell me what is transverse wave? How to explain? How to explain
The wave which the direction of vibration of the particle is perpendicular to the direction of wave propagation.
Yes, very good. The answer is correct. It's a wave where the direction of vibrations of the particles, right, perpendicular to the direction of propagation of the wave. Yes, correct. Thank you very much. Okay, let's see. Someone give answer here. This Zhong Chao Yi answer now. Zhong Chao Yi say, direction of vibration of particles is perpendicular to the direction of wave propagation. Okay, very good. Zhong Chao Yi, correct. So both of you give the correct answer lah. Okay. Okay, now I want to ask one question now. What is wave propagation now? Propagation means what? What is the meaning of propagation? Just how everyone say, like, direction of vibration particle perpendicular to the direction of propagation of the wave, right? What is propagation now? Can one you, are you here? Can one you?
Yes,
Propagation meaning is what? What is the meaning of wave propagation?
Move. Move.
Louder. Yes, move, correct. Move, movement now. Direction of movement now, which propagation mean movement. Yes, correct. Okay, come on you. Okay, so that will be the first question. And my second question here, okay, very simple one, don't worry. Cheris, are you here? Cheris,
Yes, sir.
Cheris, what is crest? Crest is what?
The
Crest is,
maximum positive point of displacement.
yes, maximum positive displacement is crest. What about trough? Cheris, trough is what?
Maximum negative displacement.
Yes, very good answer. Negative, but it's maximum but negative displacement. So you call it trough, remember? Okay. Last question. I want to call this who are? Kelvin Lim. Kelvin Lim, where are you, Kelvin?
Yes, sir.
Kelvin, okay. Can you give 3 examples of transverse wave? Example, 3 examples. Example
Ultraviolet waves, light waves, X-ray waves,
yes,
X-rays.
correct. Very good. Okay. There are many examples actually. Like you can give a water wave. Water wave is one of them lah. Water, light also including here, right? Water, light, radio wave, microwave, all these are. Okay, see, electromagnetic wave here got 7. I tell you, this 7, you have to study thoroughly one by one. No, they say you study electromagnetic itself only, you will take 1 week, 2 weeks because it's got 7 types. So you need to study radio wave, microwave, infrared, all you want to know, all the function. I'm sure you know that radio wave, microwave, all these are very important, right, in our daily life. X-ray and gamma ray some more. Because gamma ray now is the only weapon can kill the cancer cell. So all the cancer treatments to kill the cancer cell, right, cannot take medicine one. So they use gamma ray. Gamma ray can, once a gamma ray scan on the cancer cell will die. So the only cure for cancer now is using gamma ray. They say gamma is very important, gamma ray. But gamma ray very dangerous because it's radioactive one. And very effective things, but very dangerous. Okay, it will cause other side effect. Okay, so all this you know already. Okay, now we move into next one is longitudinal wave, another types of wave. Longitudinal wave. Just now was transverse. Now it's longitudinal wave. Longitudinal, okay. What is longitudinal? Okay, let's look at here. Okay, you see this diagram first. I use this diagram to explain to you. Longitudinal wave, it move like this one. You see the wave all come together, move, you vibrating left and right one, vibrate, then compress, then open up, then compress again, and then open up again, then compress again. So you see here, you have compression. Compression means all the molecules come together. It's moving horizontal one, all vibrating like that. And then here open up, then combine again, compress, open up again, compress again. It moves like that. You know this earthworm. Earthworm, you know not how the earthworm move is like that. No? The earthworm move, you see the body of earthworm when the earthworm moving, right? It will contract the body, then after that stretch out the body, contract again, stretch out the body, contract again. It move like that one. The earthworm, charging tanah, understand? So this kind of wave move like that one is called longitudinal wave. Okay, direction of vibration is horizontal. Then direction of propagation is also horizontal. In this case, I see you highlight here, wave in which direction of vibration particle parallel to the directions of wave propagation. So it's called longitudinal wave. Just now the one transverse is perpendicular. Now longitudinal wave, they are parallel. Direction of vibration parallel to the direction of propagation. Okay, so don't worry so much. In your syllabus, right, only one wave is longitudinal. So the example is sound wave. Only one example. So remember that. Only the sound. Only sound move like that. Okay, sound wave. So very easy for you to remember lah. You remember sound wave is longitudinal wave. Other wave are all transverse except sound. Okay, sound is here. Okay. So remember vibration horizontal, propagation also horizontal. So they are parallel. Okay, compression means all the molecules come together, compress. Then after that, stretch out, open up. Refraction, they call it refraction. Open up is refraction now. Okay, then compress again, refract again, refraction is open up. Okay, it's like this. I see close, open up, close again, open up. Okay, like this thing. The earthworm, you see the earthworm, how the earthworm move is like that. Okay, compress, open up, compress, open up. Okay, so this is longitudinal wave. Only one example. Sound. Only sound move like that. Remember, very easy to remember. Only sound. Okay, one example only. So remember now. Okay. Okay. Now, question time. Ching Han, are you here? Ching Han, are you there or not? Ching Han, no, don't see the microphone. I think no microphone there. Paul Siu Mei, are you there?
Yes.
Paul Siu Mei, can you explain to me? Longitudinal wave is what? Longitudinal wave.
The direction of vibration of the particle is parallel to the direction of wave propagation.
Yes, correct. Okay, it's perpendicular lah, parallel. Sorry, not perpendicular, it's parallel. Parallel to the direction of propagation. Only one example, I think you need ask already lah. Okay, so it's sound wave. Okay, okay, this one I think very simple. Okay, next one is there's a lot of wave terminologies you need to learn. Okay, the terms are amplitude. First one, highlight amplitude. You see this wave, amplitude refer to this one. This distance is called amplitude. When you ask to calculate amplitude, right? So you calculate this distance. You draw a center line. This distance is called amplitude. Okay, the meaning of amplitude highlight. Kelvin, Kelvin, I think your mic, you didn't switch off your mic.
Sorry, sir.
It's okay. You're having running nose, I can hear, you know. Your nose got problem.
Sorry, sir.
It's okay. Off it.
I got a bit sinus, sir.
Sinus,
Yes, sir.
You are in your aircon room, correct not?
No, sir.
No, sir. No, then okay lah, Okay. The amplitude is maximum displacement of medium from equilibrium position. You see, when you have a wave like this, right? You draw a center line. This is called equilibrium position. Equilibrium position means the center line. So maximum displacement from this line, maximum positive maximum or minimum positive. Okay. So maximum displacement is called amplitude. Okay, remember the name, amplitude. Remember the terms, you know. So, okay, the second one is period T. Period meaning time for one complete oscillation. Time for one complete oscillation. Okay, it's mean like this. Listen, look at this wave lah. How to consider is one complete oscillation? Complete oscillation is count like this, you know. It start from here lah. Go up, go down, go up, go back to the same position. So it started at this position. It started here, right? And go up, go down, go back to the same position. This is one complete oscillation. Like this, one up, one down. That is considered one complete oscillation. So from here to here, it takes how long? So that is called periods. Time for one complete oscillation. What is the time taken? So from here, move to here, how long it takes? So that is called periods. So remember that. Period is time taken for one complete oscillation. Okay, the second one. Third is frequency. Sorry, third one. Frequency is the number of oscillation in 1 second. What is the meaning there? Number of oscillation can be made in 1 second. Okay, I try to explain. You all listen. Period, you measure the time for one complete oscillation. That is period time. Then frequency is like this. Frequency is in a fixed time, 1 second. 1 second time. How many complete oscillation you can make in 1 second? That is called frequency. Okay. If frequency 2 frequency 2 hertz means in 1 second can make 2 lah. 1, 2. This is called frequency 2 hertz. 2 hertz because in 1 second can make 2 complete oscillation. So we call it frequency is 2 hertz. The number of oscillation in 1 second. Understand? Frequency. But usually frequency cannot be measured one. How to measure 1 second can make how many oscillation cannot, right? Cannot make one. Cannot count. So we use formula to calculate only. You want to find the frequency, you take 1 divided by the period. That's it. 1 divided by period. So remember this formula to find frequency, you take 1 divided by period. Once you know the period, you can find the frequency. Okay? Okay, frequency is number of oscillation made in 1 second. So to get the values of frequency, you calculate using this formula, 1 over period. Another formula, you can write it out. Sometimes the formula can be this, period equal 1 over F. Can be the Malay one. Okay. Same. F is 1 over T. T is 1 over F. It's the same. Okay. When you want to find frequency, you take 1 divided by T. When you want to find T period, you take 1 divided by frequency. So they are the same one. Okay. So 3 things already. Amplitude, period, frequency. And the unit for frequency is, you jot down, is hertz. H, Z, hertz. It's Z. So we pronounce it as hertz. How many hertz? Frequency unit is hertz. Okay. The next, a new thing for you to learn. Wavelength. This symbol is like the Chinese words. Symbol is you write like this. This lambda. The pronunciation is lambda, not lambda. It's lambda. This symbol you have to remember in your whole life. To write this symbol, you write like this. I show you. You write this on, then you write here like that. Okay. So it's lambda. Okay. Lambda. Okay. Lambda is wavelength. Wavelength lambda. This symbol is called lambda. You pronounce this as lambda. Understand? Okay. This symbol. So what is the meaning of wavelength then? Okay. See this diagram. Wavelength is a distance between a crest to another crest. This distance is called a lambda, one wavelength. How big is a wave? Is measured by lambda. So you want to know, right? From one wave to another wave, what is the distance? The one is called wavelength. What is the length of the wave? Wavelength. So we call it lambda. Or you take trough to trough also can. This one is also lambda. You either take crest to crest or trough to trough. Okay. So this distance is called wavelength. Okay. So the definition. Wavelength lambda is distance between 2 consecutive points which are vibrating in phase. In phase means same direction, like crest and crest, they are in phase because same direction. This one moving here, this direction. This one also moving here, same direction. When they are moving to the same direction, we call it in phase. 2 consecutive points which are vibrating in phase. Okay, or you can say distance from one wave crest to the next. I mean, this crest to the next crest is lambda. Or you can say distance from one trough to the next. Okay, trough to the next. So it's called a wavelength, lambda. So remember the definition. So you fall already now. Amplitude, period, frequency, and then wavelength, lambda. Okay, lambda is new for you lah. I believe you never heard this word before, lambda. Okay, frequency, I'm sure you heard it before. Lambda is totally new for you. Okay, lambda, wavelength, lambda. Yeah. Okay, now I give you a little bit time. You go and digest all these things first. All from the beginning here. Start from amplitude. Okay, make it bigger. The wavelength. Okay. Okay. So read all this or memorize it. Amplitude, period, frequency, wavelength. Okay. Okay, ready or not? Okay. When I call your name, so you answer. Okay, Sima, are you there? Sima,
Yes, sir.
Sima, tell me the meaning of amplitude. Amplitude is what?
Maximum displacement of medium particles from the equilibrium point.
Okay. You know how to calculate the amplitude, Okay, next. Chen Leong,
Yes.
Chen Leong, are you there? Okay,
Like
Chen Leong, what is the meaning of wavelength lambda?
got three.
Wavelength,
Which one you want?
anyone, you tell me anyone.
The distance from one wave crest to the next.
Yes, correct. Distance between one crest to the next crest. Another meaning,
The distance from one wave trough to the next trough.
yes, from one trough to another trough. Okay, the distance, so it's called wavelength. Okay, next. Next is let me find another name. Terry, Terry Go, are you here? Terry,
Yes, sir.
Terry, what is the meaning of frequency?
Number of oscillations made in 1 second.
Normally, how to determine the frequency? How we determine the frequency? Cannot measure. We cannot measure the frequency one. Normally, how you do it? How you determine the values of frequency?
Formula
Use a formula. What formula is that?
1 over T. 1 over
1 over
period.
T. F equal to 1 over T. Okay, next one is hardly you remember your own. RAM. RAM, are you there? RAM, RAM. RAM, are you around? RAM not there, no sound. Salvation, are you there? Salvation?
Yes, sir.
Salvation, what is the meaning of period?
Time taken to make one complete oscillation.
Yes, time taken to make one oscillation. So, which two are related one? Can you tell me? Out of these four, amplitude, frequency, period, wavelength, which two are related one? Now, which two are related?
Frequency and wavelength.
Frequency or wavelength are related. Yan Leong, what do you say? Which two are related?
Yes. Can you repeat the question again?
Which two are related?
What two?
Out of four, amplitude, period, frequency, wavelength, which two are related one?
I think amplitude and I think period and frequency.
Yes, correct. Now you see the formula, any relation must show in the formula. One is here, F and T, they are related one. T and F. So these two are related one. Okay. Frequency, time, these are periods, they are related one. Okay. So everything I think everyone can understand now. Okay. So we move to another few more. A lot of new things you're going to learn here in our class. Yeah, make it bigger first. Now you see here. Lambda, another method to find lambda is here for longitudinal wave. You see, we forget about this one just now. This one is for longitudinal wave. Okay, the lambda is distance between a crest and not crest here. Not crest. This CR is what? Can someone please tell me? Someone please tell me. This C is what? R is what? C is what? R is what? I don't want to tell you. I see whether you understand what I say just now or not. Someone type and see what's the type. Compression, yes, Terry, correct. C is compression. This is compress. And another one who type. Terry, refraction, yes, very good. Terry, put everyone, don't type privately. So this is compression, this is refraction, compression, refraction. Okay, lambda is distance between compression and compression. Okay, from compression to compression is also a lambda, Another one you need to learn one is from the center of refraction to the refraction also can. This is also a lambda. So many ways to find lambda one, C to C or R to R. This is also a lambda. Okay. So remember, they're very flexible one to find a lambda. Okay. C to C or R to R is also a lambda. Okay. This one is for longitudinal wave. The next one is wave speed. Speed means how fast the wave move. Okay. So when you are talking about the speed of the wave, right? So please take out this formula. V equal to F lambda. Never forget this formula. To find the speed of the wave, you take frequency multiply the lambda. V equal to F lambda. This formula is You have to stick this formula inside your brain for your whole life. V equal to F lambda. A new formula for you. To find the speed, you take V equal to F lambda. Okay? That means from this formula, you see, how fast the wave moving at the speed of the wave actually depends on the frequency, depends on the lambda. When the lambda is big, the speed is big. When the frequency is high, the speed is also high. So you see, how fast the speed the wave can travel is depends on the frequency and also depends on the lambda. So these two things very important one, frequency and lambda can determine the speed of the wave. Okay, the distance moved by the wave in 1 second is a speed lah. The wave speed depends only the medium the wave are traveling through. What is the meaning of the second part there? The wave speed depends only the medium the wave are traveling through. This means how fast or slow the speed travel, right? It also depends on the medium, Depends on the medium. For example, I give you one medium lah. Sound. Sound can travel through solid, can also travel through gas, but cannot travel through vacuum, correct not? Okay, maybe I say like this. Sound can travel through solid, can travel through liquid, and also can travel through gas. I want to ask you, see whether you got common sense or not. Everyone agree, right? Sound can travel through the solid. Solid, when you knock the wall of your house, wall is a solid. When you knock the wall, you can see the sound can travel, right? Someone put the ears near to the wall from the other side, can hear the sound when you knock the wall, isn't it? So solid can travel, can transfer the sound. Liquid can transfer sound or not? Inside water. When you talk inside the water, your friend can hear or not? Sima? Sima?
No.
And the sound travel through the water?
No.
No. That means you are in the water, your friend also in the water. You talk so your friend cannot hear lah.
Cannot.
Can or cannot?
Cannot.
Cannot, are you sure or not?
A bit only can.
Kong Fan Sin, how do you think sound can travel through water or not? Kong Fan Sin?
Yes, sir.
And can travel through water one. Sound also can travel through liquid and also can travel through gas, isn't it? Gas, A lah. Then I want to ask you, sound travel fastest in where? In solid, liquid, or gas? Just want to see how smart you are. Sound travel faster in the solid, in the liquid, or in the gas? Which one faster? Someone give answer here. I want to see what is that. Hoa Xiu Mei says solid. Hoa Xiu Mei says solid, What about others? Hoa Xiu Mei says sound travel fastest in solid. Terry, what about you? Okay, someone give answer again and see who. Ong Chao Xiang also says solid. Yes, correct. Both of you correct. So this solid. Sound travel the fastest in solid. Okay. Second fast in where?
Liquid.
Liquid. Very also solid or solid. Okay, solid. Second one is a liquid.
Yes, sir.
There is a liquid. Yes, correct. Actually, the fastest sound travel in solid, followed by liquid. In liquid, sound travel very fast, Slowest actually is every day when you talk. When you talk, your sound, your voice transfer through the air to your friend actually very slow. The sound travels slowest in the air, in the gas. Very slow. They say sometimes you talk, your friend cannot hear, very slow. When you use a wire, you talk through a wire, the wire is solid, right? You can try transfer your voice to your friend, very fast one, wire, okay, solid. Okay, That is the meaning of, we say wave speed depends only the medium, depends on the medium, you know. Actually, how fast the wave can travel is very much depend on the medium. Okay. Okay, now wave speed, I want you to remember this formula, V equal to F lambda. Okay. All right, next, wave front. What is the meaning of wave front? Okay, wave front, you see, this one is crest, trough, crest. Okay, you see now. This is a line join up all the crest you join up. This is crest and crest you join it up. So the line join up all the crest now. So we call wave front. The line, okay, you see, wave front meaning is the locus of point which vibrate in phase. In phase means near the crest, the sound move to the same direction. You see, we move to this direction. Here also move to this direction. Move here, right? So when you join up all the point, right? This is a crest, you join up. So this is wave front. So here also the same. This is a crest. This is a crest. You use a line to join them up. So the line is called wave front. Or you can join also the trough. This is a trough. This is another trough. So you draw a line to join it up. Now this line also can be a wave front. Okay, wave front. Another words means wave front is a line joining up all the point vibrate in the same direction. Or same direction. Or same direction. You join them up in the same direction. You call it wave front. Okay. Why wave front is important? Because in your physics study, right? When you want to draw water wave, sound wave, right? You don't draw like that one, you know. Okay. So actually we draw the wave, you use line, one line, two line, three, like that. So then direction is like that. So this is a drawing you are going to draw to represent water wave, you know. So what you draw, all these are wave front, wave front, wave front, wave front. So this is direction of the wave. So we draw like that one, we never draw like that one. Understand? We never draw 3D direction, 3D diagram one, you know. You want to show water wave, so you draw line 1, 2, 3, 4, then put arrow, show the direction, that's it. Okay? So that is the importance of the wave front now. This one you. So remember now, wave fronts are the line who join up all the points which are in phase. Okay. For water wave, there are two types of wave front. Okay, two types. Okay, water wave got two, you know. The one is circular shape law. Two types of wave front. One is circular. This one is circular shape. The other one is plane wave front. Plane one is straight line. You see, this is called plane wave front. Plane is straight line. Okay, circular shape, circle shape one. Okay, I want to ask you all, how to produce circular wavefront? How to produce plane wavefront? For example, water Yeah, given water, a pool of water, how you produce this wave and how you produce this wave? Also asked before in the SPM, you know. You are given a big tank of water How you produce this wave and how you produce this wave? How? Can someone answer? Lim Ching Wan Lim Ching Wan, are you there? Lim Ching Wan. Lim Ching Wan Or do you want to talk already or type for me? Lim Ching Wan. Stir it. Pause you may say stir it. Stir. Stir you can produce this one. This one. Pause you may. Stir is half correct. Half correct. Not totally correct. Half correct. How to produce circular shape? Okay, I come start with this one now. Circular shape. How to start? How to get this wave? Kelvin, how to get this wave? How you do?
I'm guessing drop a stone.
Yeah, you drop a stone, correct? Drop a stone, or you use your finger to dip the water. Use your finger, only the finger. Understand? Use your finger to dip the water. Disturb the water don't say stir lah. To disturb the water, use your finger. When you dip, use your finger to dip the water, you get circular shape. This one. This one okay, huh? So remember now. To produce circular shape, right? So you dip, D-I-P, dip your finger into the water. Okay. Next, how to get this plane wavefront? How to produce it? When you are given a pool of water, how you produce this kind of wave? Huh? How Chilling, chilling. Long time never call you already, chilling. Chilling, how to get this wave?
Use a pencil or what, drop into the water.
Use a pencil. How you drop the pencil? Vertically or horizontally?
Horizontally.
Yes, correct. You use a horizontal piece of wood. You can disturb the water like this. One piece of wood, right? Horizontal one. You can keep disturb the water. This piece of wood horizontal. You can touch the water. Keep disturbing, disturb the water. And then you can have this plane wavefront come up. Okay, so remember now, to produce circular shape, you dip the water. To produce a plane wavefront, so you disturb the water using a horizontal bar, horizontal wooden bar. Use a piece of wood horizontally, you touch the water up and down, up and down. Then you can have this already. Then I have next question I want to ask you. Why the seawater has this wave one? Why the seawater can produce a wavelength? Or maybe I say like this. Water wave is produced when the water surface is disturbed. Right now, when you disturb the water surface, either you dip it or either you hit it with a horizontal bar. So water wave is produced when the water surface is disturbed, right? When you disturb water, you can have wave. Then how come this water wave come from? Sea wave. Who disturb the water to produce a sea wave?
Wind, sir.
Wind, yes. One example is wind. When the wind blow, the wind the monsoon taufan is very strong one. Wind blow, disturb the water, right? So it can produce a big water wave. Not only that, the earth, our earth is also rotating, right? When the earth rotate non-stop, every day also rotate. When you rotate, so it will disturb the water also, the water will flow to one side, the water flow to this side. So keep disturb the water, right? When the earth is turning, it's disturbing the flows of the seawater actually. This is another reason why the seawater will never come one. It will keep moving, okay? Another reason is the movement of the earth. During earthquake, right? The earth also can move one, underground. The lands will move. Then tsunami come. When suddenly the earth, one side go down, the other side come out, then it disturb the water. The earth can move one. So once the earth is moving, it disturb the water to produce big wave. Tsunami is one of the example. Okay, it's like that. Okay, okay. So this one you know already. And now crash is what, trough is what. Just I explained already. You just highlight now. Crash is maximum positive displacement. Trough is maximum negative displacement. Just highlight, can you take out this diagram? This is crash, this is trough. Okay, just take it out. So many terms here now. Amplitude, frequency, periods. Okay. Crest, trough, wavefront, wave speed, wavelength, lambda, so many, Okay, this one done. Okay, now another two more, compression and reflection.
Sir,
Yes.
Chini Hong want to come in.
Why ne?
You have allow him.
Yeah, oh yeah, sorry lah. I didn't see lah. Sorry, I didn't see. And now I click already. Thank you, ah. Sorry lah, Jimmy Hong, I didn't see, you know. Okay, compression. Compression means compress. Okay. Region along longitudinal wave. The pressure and density of particles are higher, you know, when they compress. You see this diagram, sorry. This one compress. When you look at here, right, horizontal, right, the pressure and density of particles are higher. At here, the pressure is higher because all the molecules come closer, right? Pressure higher, density particle very close, so it's higher density lah. Okay. Okay. Next, refraction. Refraction is here. Region along longitudinal wave, the pressure and density are lower. At this area, because all the particles are open up already, so pressure become low, density also become low. So remember, no. The definition that asks you what is the meaning of compression, you must see is a region at which the pressure and density higher is compression. Refraction is a region where the pressure and the density of particles are lower. So this is high pressure, high density. This is low pressure, low density region. Okay, so that explains compression, refraction already. Compression and refractions are only for longitudinal wave. Only this wave got compression, refraction. Transverse wave don't have one. Okay, all right. And now relationship. See the graph. These three graphs very important. There's many things you need to know here. Yeah. Okay, when you look at this formula, V equal to F lambda. As I told you, this formula is very important, right? V equal to F lambda. There are two relationships here. One is the speed directly proportional to the lambda. V and lambda directly proportional. Another one is V and frequency also directly proportional. So meaning that the speed directly proportional to the lambda means the bigger the lambda, the bigger the speed. You must see, when the wave lambda is big, when the wave lambda is big, right, means the wave can travel very fast, The lambda big, so the wave also move very fast. Another one, of course, is frequency. When the frequency is high, definitely the wave can go very fast. Okay, frequency high frequency. When the frequency is high, it travel faster. Okay, so you see the two graphs, directly proportional graph. The speed is directly proportional to the lambda. Bigger lambda, bigger speed. Second one, speed directly proportional to the frequency. Okay. By the way, the frequency are referring to. So some we say frequency is the number of oscillation made in 1 second, right? Actually, the other, and from another aspect, we see frequency like this, How fast the wave vibrate. When they vibrate very fast, means high frequency. When you vibrate very slow, means low frequency. When you vibrate very fast, high frequency, right? It travel very fast, okay? High frequency. Then, frequency and lambda relationship, I see, From this formula, when you bring the F over dy, so you see, lambda and frequency is inversely proportional. See, lambda up here, frequency at the bottom. So they are inversely proportional. Lambda inversely proportional to frequency. Okay. So you see the graph is inversely proportional to frequency. What is the meaning of this relationship there? The meaning is like this, When the frequency is high, you see high, frequency high, you can see here the lambda becomes small. Not here. When frequency is high, then the lambda actually small, Then when the frequency is low here, then the lambda become big. The ballet. Okay, I'll give you one example. I can't draw here, a bit difficult to draw here. Okay, never mind, I draw a little bit. Okay, you look at here. Don't look at this answer first. Let's discuss this question first. Okay, come. This one I think very simple. A student moves the end of a long spring from side to side 4 times per second. When you see 4 times per second, it means frequency is 4 hertz. Anything, how many times in 1 second means frequency, huh? So frequency is 4 hertz. The wavelength of the wave is 0.6 meter. The lambda given now. So what is the speed? Then lambda given 0.6. You want to find the speed, V equal to F lambda, just substitute so you get the answer. So very simple, right? Straightforward. Frequency 4 lambda 0.6, so 2.4 meter per second. Okay, so this one settle. Okay, I want to explain this lah. Okay, let's say now you have the water on the tap the tap leaking water leak lah. So the water is dripping down. One take. The water dripping down. Over here you have a container to contain the water lah. So when the water is dripping down, so definitely here you can see the water wave like that. 1 second, one circle, another circle, correct not? Understand now? When this is the tap, the tap leaking now, the water leaking, understand? The water drip down. So you can produce a wave, correct not? Okay, now I don't want to draw, I want to ask you lah. When the water drip down slower, what happened here? When the water drip down faster, what happened here? Any different or not? SPM question, you know. I say it again, I want you to imagine when this water drip down slowly, one drop, one drop, very slow. So what happened to the water wave here? Another example is when the water drip down very fast. One dot, very fast. So what happened to the water wave? Any different? Kenyang?
Yes.
Any different or not? When the water drip down slow, when the water drip down fast, any different here?
I think when drip down fast, the waves are tighter.
The wave,
the wavelength is shorter.
When the water drip down slower,
wavelength is longer.
Yes, correct. Kenyang very smart, no? Okay,
Thank
actually now, this distance is a lambda. This distance is like, I cannot, very hard to draw here. This is lambda. Okay, when the water drip down very fast, this lambda will become very small. Mean the circle are very close. Lambda small. So when the water drip down very fast, mean the frequency is high. It drip down fast, frequency high. Then the lambda here becomes small. So it's inversely proportional. We say water drip down fast, high frequency. Then the lambda becomes small. Then the circle very close. When the water drip very fast, the circle here very close one, you know. So frequency high, lambda small. And another case is when the water drip down very slow, as I say, just like Kian say when it drip down very slow, then you can see the water wave here, the lambda become very big. One circle, you see the distance very big one. You see or not? So frequency high, lambda small. When frequency low, then the lambda become big. The ballet one, the size is inversely proportional. The 1 year in the SPM, they came out, you know, the diagram of the water drip down. They ask you to write experiment, relation between frequency and the lambda. Later on, you will study this one in detail. Now only I tell you a little bit only. Okay, don't worry so much. Okay, next example. This one very easy to answer this question. Radio wave travel at a speed 3 times 10 to the power. You see, this is the speed of light, you know. Radio wave travel with the speed of light. What is the wavelength of FM radio received at 200 megahertz? So speed given 3 times 10 power 8, frequency 200 mega. Mega is 10 power 6 lah. Lambda, so you get the lambda 1.5 meter. Okay, so I think I understand 1.5 meter. All right. Okay, number 3. Yeah, a long rope stretched out on the floor. One end of the rope is then shaken. You see the rope on the floor. You shake the rope, right? Then the rope will produce a wave. The graph shows the rope at particular moment. The rope vibrate at frequency 8. Given already, frequency is 8. Okay, now the question. Okay, so all the answers are here. So this is a graph lah. So the wave moving up, down, right? Amplitude, I take from here lor. So 0.5 amplitude. Wavelength, wavelength because the number given are here, so you take one wavelength, you can take so many, you can take distance between one complete oscillation. From here to here, this distance is 1 lambda. You want to take crest to crest, this is also 1 lambda. But here, hard for you to find the number, correct not? Okay, but you must know, from here, one complete oscillation, this is also 1 lambda, 0.8. Here to here is also 0.81. Okay, you have to find a number here, find a number here, then you get here is also same answer, 0.8 lah. Okay, and last, find the speed. You calculate V equal to F lambda. Frequency given 8, lambda 0.8, so 6.4 meter per second. Okay, so this is displacement distance graph. You have to be careful, This one is displacement. Here is distance. Sometimes the graph given this is displacement. This one is time. When this is time, this is no more lambda. I tell you, time. Okay, I repeat my question. You all listen carefully. There are 2 types of graph they can trap you on, Displacement, distance. When this is distance, right? This one can be lambda. Okay. When sometimes they don't give you distance, they give you time here. Displacement time. When this is time, then this one become what? If this one is time, no, not distance anymore. If this one is time, then this distance become what? Anyone can tell me? When this one change to time, then this one to become what already? Juling, any idea? Juling, if this one is time, this one become what? Someone answer already. Velocity, not really velocity lah. If this one is time, here this distance become time more. If time, one complete oscillation, so that one is called what? Can Young, do you know?
Period.
Yes, very good. It's period. Time taken for one complete oscillation, period. So remember, be smart a bit, you all must be smart, When you see this one distance, this one become lambda. When you change this one, sometimes the question can trick you change to time. Then this one no more lambda, this one become period. Time taken for one oscillation, so it's period. So be smart a bit, remember, Okay, next, number 4. Figure show the sound wave produced by a tuning fork. Okay, tuning fork means it's a fork lah. When you knock it here, it will vibrate. The musician use this one to tune the piano one, okay? It will vibrate, produce a sound like that. When you hit here, it will vibrate, produce the sound like that. Okay, tuning fork. Okay. Based on a figure, determine the amplitude, determine the wavelength. Okay, amplitude is here now. This is an equilibrium position. So the vibration is left, right, right? So draw a center line. So you take half of it, so it's amplitude. So amplitude is a maximum displacement from equilibrium position. So you take here, or you take here lah. So it's 2. Sorry. Why I put it 0.2? It should be 2 or meter. It's 2 cm lah, sorry. 2 cm. This answer is wrong. It's 2 cm. Half 4, you take half is 2 cm lah. So amplitude is 2 cm. Okay. Yeah, 2 cm. Okay, understand? So take half only, center, draw a line, divide by 2. So amplitude is 2 cm. Okay, next, wavelength. Wavelength here, there are 3 lambda here, you know. 1, 2, 3. Between this 150 cm, there are 3 lambda. This is R. This is R. R and R. Reflection, right? So 1 lambda, 2 lambda, 3 lambda. So 3 lambda, so 1 lambda 150 divided by 3, so 50 cm. Okay? Okay now? Then last, what is the frequency of the sound when the speed of the sound 330? Use this formula, V equal to F lambda. V330 given the speed. Lambda given 0.5, change to meter. You know why I changed it all? Because the speed here is in meter per second, so it's in meter. So here must be meter, change to meter. 50 cm change to meter, 0.5. So finally you get 660 hertz frequency. Okay, 660 hertz of frequency. Okay. So I think almost finished already. Okay, 10 o'clock already. So any question here? Any question or not? You want to ask anything or not? I go very slow, I won't go so fast. I think we have enough time. Okay. Anyone here got anything you want to ask? Salvation, anything to ask or not?
No, sir.
No, sir. No. Okay. Hashini? Anything to ask? Koshumei? Okay, if no questions, so I will stop here for tonight. Okay, I'll stop here now. Okay, thank you very much. Thank you everyone for follow this lesson until finish. From the beginning until finish, you follow this lesson. Thank you very much. And
Thank you, sir.
yes, thank you everyone. Okay, so take good care of yourself. Enjoy your days. Okay, I see you again on Wednesday. Okay, bye bye. I see you again.
Bye bye, sir. Thank you, sir.
Yes, bye bye. Bye bye, everyone.
Thank you, sir.
Thank you, sir.
Bye bye. Bye bye.
Thank you, sir.
Okay, bye bye. Bye bye. Yeah, bye bye.
Bye, sir.
Yes, bye. Okay, bye bye.